Lecture 3, Part 2, Variance and Standard Deviation. In this lecture, we're going to be looking at measures of dispersion. First, we'll be looking at the range, and this is the difference between the largest and smallest value in a data set. Second, we'll be looking at the variance, which broadly shows us how far a set of number is spread out from their average value. This is done by finding the average squared difference of scores from the mean score of the distribution. And the standard deviation is basically a measure of the amount of variation or dispersion of a set of values, and is the square root of the variance. So typically a low standard deviation indicates that the values tend to be close to their mean of the set, while a high standard deviation indicates values are spread out over the wider range of data. So the standard deviation and variance are more complete measures of dispersion since they account for every score in a distribution. Just one extreme score might result in a larger standard deviation, especially if you have a small sample size. And since all scores are used in the calculation of variance, the many non-extreme scores will tend to offset the misleading impact of any extreme scores. First, a simple illustration. Let's have a look at these two groups. The group on the left side is video game characters that are all lined up and are exactly the same height. The photo on the right side shows a bunch of people in a classroom, and you can see they have varying heights. So what if we ask the question, between these two groups, which group deviates more from the average? Well, in the group on the left, what we'll find is that whatever the average height is will probably be identical to every single person in that group. And therefore, most likely, the standard deviation is going to be 0, and there's not going to be any deviation from the average. However, if we were to calculate the average in this group, I don't know, we pick something here, for example, and we find some people are above the average while others are below the average. So very clearly we have more dispersion in the group photo on the right. The variance. So this is the two equations we'll be using for the variance. The first equation here is for the population variance, and this is when we're working with population data. So the sigma squared here, this is a Greek letter for sigma, and this is lowercase sigma squared, is basically what, when we see that, we assume that we're looking at the population variance. And population variance is found by taking the sum of each x value minus the mean, right? So the deviation or the squared deviation divided by the total number of observations in the sample. The sample variance, we show this with S2. And S2 is found by taking the sum of each x minus the sample mean squared, so the sum of squared deviations divided by n minus 1. In a later section, we'll discuss more in detail why the sample must have a denominator that is equal to n minus 1 rather than n. So since we have a varying equations, it's going to be very important to identify whether you're working with sample data or population data. Now, hint, most of the time we work with sample data, but there are instances where we are able to work with population data as well. The standard deviation basically is derived out of the variance. If you have a look at this formula for population standard deviation, again, it's denoted by a Greek letter, which is lowercase sigma. If you look at this equation, you'll see it's the square root of the sum of squared deviations from the mean divided by the population size. Now notice everything in this root is actually the variance, and therefore the standard deviation is the square root of the variance. The sample standard deviation is simply the square root of the sample variance. The steps to finding variance and standard deviation. So we find the variance on the way to finding the standard deviation. So the first thing we do is find the mean of the sample data set. Second, we find the deviation of each entry. Then we square each deviation. Then we add up the sum of squares. Then we divide by n minus 1 to get the sample variance. And finally, we take the square root to get the standard deviation. We'll be using a chart to fill in column by column all of these different steps. Let's try an example. The hourly wages of a sample of part-time employees at Home Depot are as follows. The first thing we need to do in the process of trying to find the sample variance and sample standard deviation is we need to start by finding the mean. So to find the mean, we would just add up all of the values in this data set and divide by 5, which is the total number of observations, and find that the mean is 17. What is the range? The range is simply the maximum value in the data set, which is 20, and the minimum value, which is 12, and we find a range of 8. Now, the next slide will give us a table of how we build to find the sample variance and sample standard deviation. Okay, so here's our data represented again. So here's our employees, and here's our hourly wages. We know that the mean is 17, so let's go in and find the deviations. So the first deviation from the mean is going to be 12 minus 17, which is equal to -5. And then we can find the rest, okay? The next step is to take each of these values, each of these deviations, and square them. Because notice, if you add up the x minus the mean, you end up with 0. And that doesn't help us find the deviations. So when we square 5, we get 25, and we go through the list and square the rest, and we get these values. Now recall that the sum of x minus mean squared is the sum of mean deviations, and we get that that equals 40. So now let's find the sample variance. Sample variance is going to be 40 divided by n minus 1, in this case 5 minus 1 or 4, which gives us a standard deviation of variance of 10. And the standard deviation is the square root of 10, which gives us 3.16. First, let's find the mean of this distribution. So we have 1, 2, 3, 4, 5. Anytime you have a series of sequential data, you can easily select the one in the middle to be your mean. So in this case, the mean of this distribution is quite clearly 3. To prove that, we can just show that if we do 1 plus 2 plus 3 plus 4 plus 5, we get 15. So then in order to get the mean, we take 15 divided by the 5 observations, and we get that the mean is equal to 3. Okay, so now in calculating our standard deviation, so what do we need? First we need to calculate the deviations. So we need x minus x bar. So first we'll do 1 minus 3, which is -2, 2 minus 3, which is -1, 3 minus 3, which is 0, 4 minus 3, which is 1, and 5 minus 3, which is 2. Now we definitely don't add this up. The next thing we do is we do x minus x bar squared. Okay, so x minus x bar squared would be -2 squared, which is 4, 1 squared, 0, 1 squared, and 2 squared. Now we add up this column. So we have 4 plus 1 plus 1 plus 4, which gives us a total of 10. Now this is basically what we'd call the sum of x minus x bar squared. So the first thing we'd find on our way to the standard deviation is we would find our sample variance. Okay, and the sample variance is denoted as s squared, and the equation is the sum of x minus x bar squared divided by n minus 1. So s squared in this case will be 10, which we already found in the previous step, divided by 5 minus 1, or 10 divided by 4, which equals 2.5. So to get the standard deviation, which is the square root of the variance, so the standard deviation is the square root of the variance, so we would take the square root of 2.5, and s would be equal to 1.58. Okay, so our standard deviation is 1.58, and our mean is 3. Let's do another data set. So here's our second data set. We have 1, 3, 5, 7, 9. First, let's start off by finding the mean. So to find x bar, we do 1 plus 3 plus 5 plus 7 plus 9 divided by 5. And the mean is equal to 5. Okay, so next we do, in our process of finding our standard deviation, first we do x minus x bar. So we start out by 1 minus 5, which is negative 4, 3 minus 5, negative 2, 5 minus 5, 0, 7 minus 5 is 2, and 9 minus 5 is 4. Okay, I'm just using strictly symmetrical data just to make our calculations a little simpler. Next step, let's do x minus x bar squared. So this is the squared deviations. So now we have 4 squared, which is 16, 2 squared, which is 4, 0, 4, and 16. Right, so let's find the sum of our squared deviations. So 16 plus 16 plus 4 plus 4, which equals 40. So first let's find the variance, s squared, and recall that the equation is sum of x minus x bar squared divided by n minus 1. So the sum of x minus x bar squared in this case is 40, and we're going to be dividing by 5 minus 1, which is 40 over 4. So the variance is going to be equal to 10. Now the standard deviation, s, remember, is the square root of the variance. So it's the square root of 10, which is equal to 3.16. Okay, let's compare data sets, their means, and their standard deviations. So here we have represented data set 1 and here data set 2. Recall that the mean of data set 1 was 3 and the standard deviation was 1.58. And notice that the data in data set 1 was in a sequential order 1, 2, 3, 4, 5, and therefore the data was really, really close together, and therefore you ended up with a very small standard deviation. Right? In data set 2, we had a slight gap between our observations, and therefore we ended up with a slightly larger standard deviation. Let's look at what standard deviation means in terms of distance and movement. So let's start here with data set 1, and let's start at our initial point, which is our mean in case 3. Now let's add 1 standard deviation to our mean. So this is moving 1 standard deviation above. We'll call this 1s, or 1 standard deviation above the mean. If this was a population data set, we would call this 1 sigma, or 1 standard deviation above the mean. So what does that mean? Well, this would be the point where we take the mean plus 1 standard deviation, which is 1.58, and the value of 1 standard deviation above the mean would be equal to 4.58. Now let's do 1 standard deviation below the mean. So this is going to be the mean, x bar, minus 1 standard deviation, or 1s. Now this will be 3 minus 1.58, which is equal to 1.42. Okay, now let's go one more standard deviation. Let's go 2 standard deviations above the mean. So this will be the mean plus 2s, or 2 standard deviations. So here we'll do the mean plus 1.58 times 2. Or we could simply do 4.58, which is the mean plus 1 standard deviation and plus another standard deviation. And this will be equal to 6.16. So for us to describe what value denotes 2 standard deviations above the mean, we would say 6.16. Now let's go 2 standard deviations below the mean. So we have x bar minus 2s, or 2sd. So this will simply be the 1.42 minus 1.58. And now notice what's going to happen here is we're going to go into negative territory with negative 0.16. Let's repeat this exercise for data set 2. So in data set 2, we start here at x equals 5. So let's go 1 standard deviation above. So we have x bar plus 1 SD. Now in this case, we'll do 5 plus 3.16. So this is 8.16. Let's go 1 more standard deviation, x bar plus 2 SD. And this will be 8.16 plus 3.16, which gives us 11.32. Now let's do the other side. So we have x bar minus 1 standard deviation and x bar minus 2 standard deviations. So first we have 5 minus 3.16, which is 1.84. And then we have 1.84 minus 3.16, which is negative 1.32. Now, if we simply just look at the range here within 2 standard deviations, right, we will see that if we drew these a little bit more to scale, that the data set 1 is far more clustered around the center than is data set 2. So there's less cluster, and in this case we'd say, if we were to compare the two, we'd say there is more dispersion. This is a chart showing us 3 data sets that have an identical mean. So let's say the mean is exactly 0 in these 3 data sets. But what's happening in them is that the standard deviation is much larger in the blue data set. Notice it's very flat and extends out very far in the number line. And the red is actually a very small standard deviation. So the size of the standard deviation tells us how closely the data is clustered along this central point. The next thing we want to think about is how we interpret the standard deviation. So one of the ways we look at how we interpret the standard deviation is by using what's called Chebyshev's theorem. So remember that the smaller the standard deviation, the closer are the observations to the mean. First, what is Chebyshev's rule? Chebyshev's rule applies to any data set regardless of the shape of the frequency distribution of the data. So what is Chebyshev's theorem? Chebyshev's theorem states that for any set of observations, the proportion of values that lie within k standard deviations of the mean is at least 1 minus 1 over k squared. And that, in fact, is going to be in percentage terms. And this is where k is constant greater than 1. We can never use, we can't use a standard deviation of 1 while using Chebyshev's theorem, because you'll notice that the equation just disappears. So let's use our hourly wage data from earlier in the video to calculate what percentage of the data falls within 2 standard deviations from the mean. So in this case, k is going to be 2, so let's plug in k into 1 minus 1 over k squared. And we get 3/4 or 75%. So basically, this states that at least 75% of the data is within 2 standard deviations from the mean. So what does this mean? Given that our mean is 17 and the standard deviation is 3.17, 75% of the data falls between 17 minus 2 times 3.16 and 17 plus 2 times 3.16, or between 10.68 and 23.32. And if we actually went back to that data set and looked at that chart distribution, we'd find that basically all of our data fit into that data set, right, into this range between 10.68 and 23.32, because the fact from 12 to 20. And so, in fact, this is a correct statement because at least 75% was within 2 standard deviations. This is just a few guidelines here for k equal 2, 3, and 4. So when you're looking for k is 2, then at least 75% of data is within 2 standard deviations. At least 89% of the data is within 3 standard deviations, and at least 94% of data is within 4 standard deviations. What's nice about Chebyshev's theorem is that it doesn't make any assumptions about the distribution and what the distribution looks like. It works for skewed distributions or symmetrical distributions. Unlike the next type of rule we'll be looking at, called the empirical rule. So Chebyshev's theorem is usually used when the shape of the distribution is not known or is not normal. The empirical rule is used when it's symmetrical or normally distributed. So what the empirical rule says is that when you have normally distributed data, let's say in this case x is equal to 0, that within 1 standard deviation, which is from -1 standard deviation of the mean to +1, you have 68% of your observations. Within 2 standard deviations, between -2 and +2, we get 95% of our observations, and within 3 standard deviations, we get 99.7. This rule is effectively one very useful tool for thinking about outliers. Typically, we say when you get an observation that is greater than 3 standard deviations from the mean in either direction, that typically it's an outlier. We will look at all the details of the empirical rule later when we get to lectures 8 and 9. So this is just a little bit more guidance on the empirical rule and more specificity. Please have a look in your notes. The next slide will present a video of Chebyshev's theorem and compare that to the empirical rule.
The variance and standard deviation help us understand the spread or dispersion of a variable. In comparing two variables, the variable with the smaller standard deviation will be less spread out. So we can have two variables with the same mean, but variable 1 has a smaller standard deviation than variable 2. So the data for variable 2 will be more spread out, as you see here in these graphs. Now to Chebyshev's theorem, which says the portion of values in a dataset within k standard deviations of the mean is at least 1 minus 1 over k squared, where k is a number greater than 1. In simple terms, what this means is that you can plug in any number for k greater than 1, and this formula will give you a percentage. That percentage is at least the percentage of values in the dataset that will lie within whatever number you plugged in for k standard deviations. For example, if we plug in 2 for k, so 2 standard deviations from the mean, the formula gives us 75%. So at least 75% of the values in the dataset will lie within 2 standard deviations of the mean. And 3 for k, 3 standard deviations from the mean, gives us 88.89%. And this theorem can be applied to any distribution regardless of its shape. So let's say we have a dataset with a mean of 122 and a standard deviation of 12. We can draw a line, and here in the middle mark x bar, the mean of 122. One standard deviation to the right is 134, which we can label x bar plus 1s, where s is standard deviation. 2 standard deviations to the right is 146, x bar plus 2s. And 3 standard deviations to the right is 158, x bar plus 3s. 1 standard deviation to the left is 110, x bar minus 1s. 2 standard deviations to the left is 98, and 3 standard deviations to the left is 86. With what we computed earlier, we know that at least 75% of all values in the dataset will lie within 2 standard deviations of the mean. So in this example, 75% of all values in the dataset lie between 98 and 146. And at least 88.89% of all values in the dataset lie between 86 and 158, which is 3 standard deviations from the mean. And again, keep in mind this theorem applies to any distribution regardless of its shape. Now for the empirical rule, which applies only to a distribution that is bell-shaped or normal, like the example on the screen. It states that approximately 68% of the data values will lie within 1 standard deviation of the mean. Approximately 95% of the data values will lie within 2 standard deviations of the mean, and approximately 99.7% of the data values will lie within 3 standard deviations of the mean. So if we have a data set with a mean of 88 and a standard deviation of 11, approximately 68% of all data values will lie between 77 and 99, or within 1 standard deviation of the mean. And approximately 95% of the data values will lie between 66 and 110, or within 2 standard deviations of the mean. And approximately 99.7% of the data values will lie between 55 and 121, which is within 3 standard deviations of the mean. Alright my friends, hopefully this video helped you out. I do have more videos right there for you. Till next time, I am.
This is the end of Lecture 3, Part 2. Please complete your quizzes and homework assignments and be prepared for our Zoom session next week.
I'm here.